We've got our TensorFlow basics down now. We have built some graphs in TensorFlow. We've created a neural layer in TensorFlow. Now it's time to build some models. We're going to take baby steps here to go through the ins and outs of learning. So instead of starting with a big, deep neural network, we're going to start with a simple line. So I've already created this notebook for you. It's in the point-by-point intro to TensorFlow notebook here. We're going to recreate it here for this demo so we can talk everything over. So we're going to call this point-by-point intro and give it a catchy title. Point intro to TensorFlow. Now, this idea and the basis of this code is by a gentleman named Jared Ostermeyer. So he has his naked tensor code, and I think it's this brilliant way of introducing TensorFlow. So we're going to follow his lead there. So we're going to load our dependencies as before. We're going to import NumPy, as we always have been, setting the random seed to 42. And then we're going to need a few different libraries. We're, of course, going to import TensorFlow now. That's what we're working with. We're going to set our seed for TensorFlow as well. And we're also going to do some plotting. So we're going to import matplotlib. And we are going to be working with data frames just a touch for my convenience. And so we're going to use pandas for that. That'll all be real simple uses of those tools. So first we're going to create our data. So this data set is super small. These are just X's and Y's. I'm going to copy them out of the existing notebook so that we're not wasting time typing in data. So we have X's. Our X's are simply the numbers 0 through 7. And those are the features in our model. And we have an array of Y's as well. And so those are some random values. Let's have a look at how X's predict Y's. It'll be easiest on a chart. So this is just some quick syntax here for creating a figure with matplotlib. We're just going to make a simple scatter plot of X's on the y-axis and Y's on the y-axis. Why not? And we can see a clear relationship as X's get larger, Y's get larger from -1 to 1. So this is the line that we're going to try to learn here. So as with any of the TensorFlow graphs that we've been working with so far, we need to define our variables. The variables that we're going to learn are the slope of the line, which is traditionally denoted with an m. So we need to initialize m with some random variable, just like when we're initializing a neural network, we have to use Glorot initialization or some other kind of initialization to decide on the initial random values. So we're going to do that here as well. You know, clearly we can see that there's a positive slope here, but we don't want to let this model here cheat. So we're going to make its life a little more difficult. We're going to say that there's a negative slope as a starting value, not too far away from 0. And we're also going to have a y-intercept. And we can see that the y-intercept here is around -1, but we're going to initialize it with a slightly less easy random initialization here, which is just the value 1. And you can put any values in there as long as they're not too far away from 0 when you're running this code notebook yourself. So the next thing we want to do is define our error. So we're actually going to define our cost function. So previously we were using pre-made functions to do that, but here we're going to have a chance to understand how cost functions work a little better. Because it's easier to code up, we're going to work with quadratic cost, even though we know it's not quite as efficient. So we're going to accrue some total error. Before we start, that total error is 0. And we're going to zip together our x's and our y's so that we can work with them side by side in a single object. And then we're going to say our predicted output, so our predicted y, which often people call y hat, is predicted by the slope of x times x plus b. So that's a line, y equals mx plus b. It's a very standard definition of a line. And then we also want to add to our error. So our total error will be added to. So we're going to iterate over each of the values in x and y. So for x and y in the zip together x and y. So going step by step, point by point over each xy pair, we're going to go through this model just as if we had our big neural network all built up. This is just a small little model here. And then we're going to assess our error at the end of the model. And that is quadratic cost, as we said. And so we take the difference between the y that we expected. So we're looking to get these y values. And our model will have some output. So whatever the difference is our error. But we're going to square the error, which has two effects. The first effect is that it makes all of our errors positive, because when we take the square of a positive or a negative number, we end up with a positive number. And then the second thing is that because we're squaring it, small deviations between y and y model won't result in a very big error. But large deviations, when those are squared, will become exponentially larger. So we're particularly penalizing the large error, and this is just standard quadratic cost or mean square error cost, to use another way to phrase it. So now we have defined our model, we have defined our error, we simply now need to define our optimizer. We're going to use gradient descent, as we have been known to do. So define optimizer. We're going to define our optimizer op, or operation, as gradient descent. So we'll pull that out of the TensorFlow library here, our gradient descent optimizer. And we're going to set that with a slow learning rate. And we're going to have it set to minimize the total error. So we're specifying a gradient descent optimizer here to learn, and it's going to learn quadratic cost. We're setting it to minimize quadratic cost step by step, and it's going to take pretty small steps with learning rate at 0.001 to minimize that cost. Now, I said in the last notebook that we always need to define an initializer op, so we'll do that. And that's just simply an initializer operation. And so that is just figuring out how to arrange all of our variables in the global environment here when we run the computational graph. And then we are ready to execute our session. So execute session. And in that session, we can train. So as we have been doing so far in TensorFlow, we need to create an instance of a session here and do all of our work within it. So the first step, as we've been doing in every notebook so far, is to initialize the graph with our initializer operation. And then we need to define our number of epochs, so the number of times that we're going to run through all the data to learn the slope of the line and the y-intercept of the line. So let's start with a small number of epochs, just going through 10 times. And so for I, for the iteration, in range and epochs, so cycling through our data 10 times, we're going to run our optimizer operation. So 10 times, we're going to go through this process of feeding x, multiplying it by m, which is starting off as this negative 0.5, and then we add the y-intercept, which is starting off as 1. That comes out with some value for y model across all 8 of our input x's and y's. And then we get a total error, a total cost associated with that single epoch. Then we use our gradient descent optimizer to try to minimize this error. We do that 10 times over the course of this for loop. And then when it's done, we want to get our slope and our intercept out of it. So we do that by fetching, using fetches in the data in and out section here. And we can specify multiple fetches. We haven't done that yet inside of a list or a tuple. So we do that with square brackets or round brackets. And so now we can see what its guess of the slope and the intercept should be after 10 epochs. Now, we can see by looking at this graph that the slope is positive and that the y-intercept is around -1, but we're getting results nowhere near that. So we have a negative slope and our y-intercept is way up here. So it hasn't deviated too far from our random initializations in 10 epochs. But we can fix that. We can run for more epochs, of course. So let's run this whole graph again, running over 1,000 epochs. And here we go. All right. This is starting to look pretty good. So we have a positive slope of 0.3. That sounds reasonable. And we have a y-intercept down here, much closer to -1. So this is starting to look like a well-fit result. It seems like we have succeeded in approximating the line. So let's have a second look. So let's calculate our results. So our y hat, our estimates from the model, are equal to the intercept plus the slope times x, and we have to wrap x in a NumPy array here to execute this line. And then we can create a pandas data frame to look at the real true y's against the y hat. And we'll just assign some nice column names for ease of readability, y and y hat. And then we can see the estimated values of y hat are roughly in line with y. So it's doing a pretty good job. And we can actually create another little plot here now where we fit the line that we have learned, and we can see visually how good this looks. So we're going to create a scatter plot with our x's and y's. We're going to define a minimum and a maximum range for our x values. This is just for the aesthetics of the plot. And we're going to do the same thing on the y-axis. Just create a plot of the correct size here. And then we plot out all the data. So x min, x max, y min, y max. There's this quick little thing here. And here we go. So there's our plot, and it looks pretty good. So we fit a pretty good line here. Pretty happy with that. If we had stuck with our initial result after just 10 epochs of training, which we're pretty confident wasn't enough, we can see what the results would have looked like. So we run this session again. Just takes a second. And yeah, clearly that is not a good fit after just 10 epochs. After 1,000, looks pretty solid. Now there's one other parameter I want to illustrate here. So we had our learning rate set to 0.001, and that's a slower learning rate than we were using in any of our neural networks earlier in these live lessons. So what happens if we increase it to 0.01? Will we have a better fit if we go more quickly here? Or will we be able to converge on the correct answer more quickly? So, no. In fact, the results are crazy. So it doesn't work at all to be learning that quickly. We're unable to find a decent look at it. It's guessing that the slope is negative 265 and the intercept is negative 53. These are crazy numbers because the gradient descent optimizer is taking steps that are far too large, and so it is missing the minimum cost by miles. So that was a simple intro to fitting a line with TensorFlow. Now we're going to do things a little bit more cleverly. We're not going to find the fit of the line by fitting things individual point by individual point. We're going to leverage the power of tensors here a bit. So on one hand, it's a lot more elegant than using a for loop in our code. And then the second thing is that once we're building larger graphs, by using tensors, it enables us to leverage the power of TensorFlow distributing the graph across however many devices we can do the computation on, however many CPUs or GPUs we have. So let's set this up. The notebook that I've already created that does this is available for you in the TensorFied Intro to TensorFlow right here. And we are simply going to modify our point-by-point intro here to accommodate the tensor. So the first few cells are exactly the same. It's in this fifth code cell here that we're going to start making our changes. So instead of using this for loop, we're going to get rid of that way that we're calculating total error, and we're going to strip out this for loop, and now we're going to calculate our y model the same way, but instead of doing it with individual x's from the x's array, we're going to use the x's array itself, and then we're going to define the total error in one step using a TensorFlow operation, which is reduce sum. So the idea here is to take all of the values here across all of the x's and y squared errors, and then we're summing them and reducing them into a single scalar value. And instead of doing that individual y by individual y, we're doing that with y's here. So just for the sake of consistency in our nomenclature, let's call these y's as well. So there we go. And the remaining steps are identical to the notebook that we'd already built. So let's head up and restart and run all of our cells again to see what happens. Well, of course, we left our learning rate too high, so the results are wacky. Let's restart and run that again. And with the lower learning rate, we should be all set. We need to train for more epochs. So let's set that to 1,000. And go. Beautiful. Look at that. That's a perfect line fit around those points. That's exactly what we were hoping for. So having done all that with this small data set, that's all fine and good. Typically in TensorFlow, though, we're not working with these small data sets. We're working with thousands or millions of data points. So we're going to rebuild and resolve this problem using tensors as we did in this last notebook, but we're going to set things up so that we're solving with not 8 data points, but we're solving a line with 8 million data points. So I have this notebook built for you already, as usual, in this Intro to TensorFlow times a million notebook. But we are going to rebuild it quickly now. So there are enough changes that it's worth doing this quickly from scratch. So TF intro 1,000,000 demo, and give it a catchy title here. Times 1,000,000. And so we have the same dependencies. So let's pull those over from our previous intro. Except that we don't need, no, we'll still use pandas actually. So that's all loaded. This time, our x's aren't going to be manually defined as 8 specific values. They are going to be still values between 0 and 8, but we're going to have 8 million of them. So this linspace function in NumPy allows us to create these 8 million points spaced over the intervals 0 to 8. And we're going to create our y data set to have a slope of 0.3. So m times x plus b, and our b is going to be negative 0.8. So y equals mx plus b with b of negative 0.8. And then, so that we don't just have our y's fitting that perfectly, we're going to add some random noise. So we're going to use this random normal function here to create jitter around the line. So there we go. That may take a moment on your machine to run. And then let's have a look at how that looks. So we can plot out our data here to have a look. Like so. We're going to create a subset of the data because to create a plot with 8 million points is a bit silly, and we won't be able to see anything. It'll just be a blur of points. So we're going to create a little pandas data frame here of our data and sample from it just 1,000 points. And this is an important syntax here. I just want to be able to create the plot so that you can see what's happening. So we're going to create a scatter plot with x on the x-axis from our data subset and y on the y-axis from our data subset. So let's have a look at that. It'll take a moment to generate. And look at that. There's 1,000 of our 8 million points. So let's solve this line as we did before. So we're going to define our variables as we have done in all of our TensorFlow notebooks. So we're going to initialize our slope variable with the same random value as we were choosing before, as well as our y-intercept. And now that we're working with 8 million data points, we probably want to be using some of the tricks as we were using with our larger deep networks earlier. So we want to be using batches for stochastic gradient descent. So we want to define our batch size. Let's work with batches of size 8. It seems like a nice number we've been working with lately. And then we need to define our placeholder tensors to hold the data once we start feeding it in. So we need a placeholder for our x values. And as before, those are going to be single point precision numbers. And the placeholder is going to be the same length as the batch size that we decided on just above. And our y's placeholder is going to be the same. So everything about that placeholder definition is identical to with the x's. So we can execute that line. Now we have our placeholders, we have our variables for our graph. So we simply need to define the graph. So we have, as on the previous notebook, we have our model y's, so our predicted outputs from the model, which are y equals mx plus b, as before. And we're defining our error in the same way. We're going to be using our quadratic cost once again in the same way as in the previous notebook by reducing the sum to a single scalar value, and it's the difference between the values being fed into the graph and the values being guessed. So we define that there. And once again, we need to optimize. That's going to work in the same way as in our previous notebook. So let's just grab that code and paste it in here. We need to have an initializer operation, and that's the same as in our last notebook. So let's just post that in here. And now we need to build our graph while sampling. So we need to do things a bit differently here than we were with just 8 data points. So we start off in the same way by creating an instance of a session. We need to run the initializer operation at the top, as we have always been doing. And we need to decide on our number of batches that we're going to run over. So we can start with 10 to make this quick and easy at first. And then for I in the range of our batches, we're going to do our work batch by batch. So we're going to select a random 8 values from the 8 million. So to do that, we're going to use the randint function in NumPy, and we're going to sample from all of our x's. We're going to grab a batch of size 8 as we defined above. And now we need to feed some data into the graph, and as we have always been doing, we do that with a dictionary. So our placeholder value will be filled with the random x's that we chose, and our y's will be, our y placeholders will be filled with the random y's that we chose. And then we need to actually run a step of our initializer operation, of our optimizer operation, sorry. And we need to feed in our dictionary here. So we are all set, and we want to fetch something from this operation as well. So we're going to fetch the slope and the intercept as before, and you can specify the variables that you want to fetch by enclosing them in either a list or a tuple. We'll do it in a list here. So we're all set. Let's see what our slope was and our intercept. So we have only run for 10 batches, and you can see that our results are not very good. So once again, we have not deviated very far from our initial values in just 10 batches. But what if we do the same things before, and we increase our number of batches that we run through from 10 to 1,000, and that should be enough training to get a decent slope and intercept estimate. Takes a little bit while to run. And here we go. We have our slope. So we input a slope of 0.3 up here, and indeed, that is the slope that we have coming out of our model. We put in an intercept of negative 0.8, and we have a pretty close approximation of that as well from our TensorFlow line fitting model here. that's it with these kind of demonstrations, getting us used to how TensorFlow works with these simplified examples. Up next, we're going to be building deep networks with TensorFlow.